All right, so in this video, we'll wrap up section 12.3. So I'm going to do a couple more examples. I'm on page 776 of your textbook. I'm going to start with number 14, which says, in exercises 1 through 16, find the derivative of the function. So they want us to find the derivative of the function f dot g. So they want us to find this. Where f is given by the vector whose first entry is negative 2t over the quantity 1 plus t squared. And the second entry is 1 plus 2t, the quantity 1 plus 2t squared over the quantity 1 plus t squared. And g is equal to the vector whose first entry is the quantity negative 2 minus 4t squared over the quantity 1 plus t squared quantity squared. And then the second component is negative 4t over the same quantity 1 plus t squared quantity squared. All right, so those are the two vectors. So now, according to the product rules that are in you all's textbook, we have two different ways of going about computing this. The rules of derivatives from this section tell us that if we want to take the derivative of this dot product, so we can do it that way. We can just take the dot product, which we all know how to do, and then take the derivative. Or it tells us we could take the derivative of the vector function f and then dot that with g, and then add to that f dotted with the derivative of g. So we can do it either way, whichever one, and it's just depending on the problem which one ends up being easier. And a lot of times you really can't tell beforehand which one of the two is going to be easier. Sometimes you can, or you might start the process and one side seems difficult and you just switch gears and do it the other way. I'm going to, I would guess that this left side is going to be easier in this scenario, but I probably would always guess that from what this looks like, but that won't necessarily be the case. I'm going to use the left-hand side and will abandon ship if it doesn't work out very nicely. All right, so we want to compute this dot product. So f dotted with g. So we have negative 2 times the negative 2 minus 4t squared. So here we're going to end up with 4t plus 8t squared, t cubed, over 1 plus t squared quantity cubed. We're going to have the same denominator there, so I can just put all this together. Then over here, we're going to end up with negative 4t, then minus 8t cubed. So yeah, this works out nicely. This is all over. So I just looked at the fact these denominators are the same and those denominators are the same. So we're just making one common denominator for the sum, because it's really this times this plus that times that. So this is 1 plus t squared quantity cubed, but the numerator is 0 though. So this equals 0. And this is not the 0 vector, because remember a dot product gives us a scalar. And now the derivative of 0 is just 0. So f dot g prime is just going to be equal to 0. And that's our answer there. And we would have gotten the same thing had we gone about it this way. All right, now one more example from this section. We will do number 49 on page 777. So 49 says a ping pong ball rolls off a table 2.6 feet high with an initial speed of 2 feet per second. Part A, how long after it leaves the table does it hit the floor? Note that the velocity vector is horizontal when the ball leaves the table. At what speed does it hit the floor? Okay, all right, so let's sketch. I'm going to sketch a table. Let me find another. And I'm going to sketch a set of coordinate axes. So our table will be red. I'm just going to sketch the corner of a table, and that corner of the table, or the leg of the table that will be directly below that corner, will be our z-axis. So now our set of coordinate axes. So this is my tabletop, or a corner of my tabletop. And then we have our coordinate axes. So it's our x, our y, and our z. And it said that we have a ping pong ball rolls off the table 2.6 feet high. So this is 2.6 feet, that distance. I'm not going to draw it there or label it there, but I'll specify that a little bit later when we need to, and whatever vectors we have to use, with an initial speed of 2 feet per second. So they tell us, note that the velocity vector is horizontal when the ball leaves the table. So there's a ball on this table. There's a ball that's going to drop off this table, and I'll put it at the corner of the table, but we don't necessarily have to be at the corner, just make our lives easier. So there's the ball right there, and let's put some dots or something on that ball so we don't think it's a 0. All right, so there's a ball that's about to roll off the table. They're saying that the velocity vector is not going down. It's going, or in some diagonal direction, it is going in the horizontal direction. So velocity vector is on top of the table, like going that way or coming this way, it doesn't matter, but it's on top of the table. It is not going down in the z direction at all, nor is it moving up in the z direction at all. So to make our lives easy, I could say the velocity vector is coming this way on top of the table, but let's just make it go either directly in the y direction or directly in the x direction. Doesn't matter which one you want to use. I'm going to make it go directly in the y direction. So now I know what this vector is. I know it has magnitude of 2. Yes. So I know this has magnitude 2 and it's moving in the y direction. So this vector right here is just the vector. That's my velocity vector of the ball at time 0. So v sub 0 is 0 because it's not moving in the x direction at all because I chose to draw it that way. Then 2 in the y direction, and then it's not going in the z direction at all. So 0 there. So that's the velocity vector for that ball. Now, what else did they give us? I know this is 2.6 feet. How long after it leaves the table does it hit the floor? All right, so we also, from this, can look at what its initial position is, because I put it right directly above the origin. So its initial position, according to the way that I set this up. Now, you could set it up other ways. You will probably complicate things more. So for instance, I could put the corner of the table directly above x equals 7 for whatever reason. You're still going to get the same answer if you do everything correctly. But it's easier to just set as much stuff over the origin as you can. So 0, 0, and now that's where that 2.6 comes in. So now I have my initial velocity and my initial position. All right, so now we're going to use an example from the textbook, which is on page 775. They give us what the position of an object at any time t would be under these circumstances. So they tell us that r of t equals -1/2 g, where g is gravity, t squared k, and I'm going to write it the way they have in the book, and then I'll change it to the way I tend to write stuff, plus t times the vector v naught plus r naught, the vector r naught. All right, and this is from example 10 on page 775. This is from example 10 on page 775. All right, keep forgetting what we were asked to do. We were asked, how long after it leaves the table does it hit the floor? So part A of this problem, actually, I said I was going to set this up in the way that I normally write it first. So let's write out what is our r of t. So for us, r of t equals, what is our I component? So because they have a k here, this is an entire vector. So it has a k, an I, j, and k in it, and this has an I, j, and k in it. So I'm just going to go and put these things together and put them in the pointed brackets the way I tend to write vectors. So now for us, gravity, because of the units they gave us in this problem, we're not using 9.8 meters per second squared because they gave us stuff in terms of feet. So we need to use slugs, so 32 slugs. So G is going to be 32 for us. It's not going to be 9.8. So make sure you pay attention to what units you were given. If we had been given metric units, then we would use 9.8 right here. All right, so now let's look at our vectors. There are no I components here. The I components in velocity times t. The I component in velocity is 0 times t, so that's going to be 0. And then the I component here is 0. So in our I of t, we get 0, which makes sense because nothing in our picture is moving in the x direction at all. Now, no j components here. J component here is 2 times t. So that's what we get from there. And then plus what is the j component here is 0. So we're just going to have 2t right here. And then k components, the k component here is -1/2 times 32t squared. And then k component here is 0. And k component here is 0 times t. K component here is 2.6 from right there. So we get -1/2 times 32t squared plus 2.6. Sorry, I'm squeezing this on here, plus 2.6. All right, so that's what our position vector is at any time t. So 0, 2t, -1/2 32t squared plus 2.6. So now part A asks us, now translate what they said to when is, because they ask us when the ball hits the ground, when is the height. And for us, height is our k component. So k component of r of t. Zero. So that's what we were asked. When is the k component of r of t 0? So in order to answer that, we're just going to solve. We're going to take our k component, which we have here, set it equal to 0, and solve for t because it asks us when. So solve -16t squared plus 2.6 equals 0 for t. And I'm not going to go, for the sake of time, I'm not going to do this because I'm running out of time. And then part B, so you would solve this for t. Part B says something. At what speed does it hit the floor? All right, so we know at what time it hits the floor from part A. So part B, you want to find at what speed it hits the floor. So part B, we're gonna find r prime of t. So find v of t and plug in. You're gonna find v of t, and then you can plug in the t at that point and then take the magnitude, or you can take the magnitude first and then plug in t, doesn't matter. And plug in t from part A. Then find the length of that vector. All right, so if you get stuck on any aspect of that, or you have questions about any aspect of that, since I had to kind of scramble through at the end, feel free to either post a discussion or send me an email, and I'm happy to fill in any gaps of and understanding on that problem. All right, so that's it for section 12.3, and we'll start 12.4 in our next video.